All right, thanks for inviting me. My pleasure to be here. This is a great topic. I almost didn't make it here. I broke one of my cardinal rules. In the winter, don't travel through Chicago. But I did arrive finally this morning. So one of the grand challenge problems of our era is the links between statistics and computation. You've already heard a number of great talks about that. I know that Nesterov talked about that, and Wainwright and Fahn. When you say computation, you might think that you'd go to computer science, complexity theory, and all that. But really, what's happened is you tend to go to optimization. The computational model there is a little more limited. The computer science one is broad. It's all of computation. And to get useful bounds and constants and meaningful rates and all that, the optimization connection has been, I think, to date at least, more productive than the complexity theory one. So I think of those communities as really cooperating, statistics and optimization. And also in this talk, there'll be a fair emphasis on the systems community. Why are we studying things that are distributed and asynchronous and all that? Well, because the computing platforms of the day are of that form. And so people have been building highly parallel, high distributed platforms, and they're really useful now, and they're the only way to go if you have really large scale problems. So this is going to be a theory talk. I've become much more of a theoretician over the last few years because I think those are actually where the challenges are. A lot of my colleagues in machine learning are going the empirical direction and trying things out and all that's great. And I'm headed in the other direction because I just think there's some super interesting, deep challenges on the theory side. Just to kind of dig into that a little bit, in modern optimization and large-scale data analysis, the blend of those two things, we all have to think about parallelism, and that's challenging. There's not a general theory of parallelism in computer science just to borrow, so we have to kind of invent our own. We have stochasticity present in many ways. We want to exploit it and control it. We have asynchrony to worry about, and that could cause a great deal of difficulty for analysis. It may be helpful, it may be harmful, but we have to get our hands on it theoretically, and that's hard. And then we have to try to go fast. So we need to understand how fast we could possibly go, and can we go that fast, and maybe even in some sense go faster. So that's the theme, that's what the talk's gonna be about. All right, so if I get through all this, there's five little vignettes here I want to talk about. The first one is on how fast can you go. This is joint work with a person who's actually in the audience, Andre Wibisono and Aisha Wilson. And we'll talk a little bit about so that work is not stochastic, but it's about lower bounds, and it's about kind of the mathematics of lower bounds in some sense. Now, then we'll bring in some stochasticity, then we'll bring in some asynchrony, making our problem even harder. Then we'll bring in the full distributed paradigm, where it's really a lot of asynchrony. And then if I have time for some dessert, I'll talk a little bit about non-convex optimization, a very recent work just this week on avoiding saddle points quickly. So let me start part one. This is, again, joint work with Andre, who's sitting here, and Aisha Wilson. So we're going to go back to Nesterov acceleration and think about that from a physics point of view, if you will, a variational point of view. All right, so you don't need that slide. We're going to do, for this part of the talk at least, convex optimization, unconstrained. And you all know what classical gradient descent does. We're going to assume that beta is given by some oracle, and we know that the convergence rate is 1 over k. If you've seen k steps, you're within 1 over k of the optimum. Nesterov and others, many years ago now, thought about how you get lower bounds when you're only allowed to look at gradients, and your computational model is something like you take something in the linear span of the gradients you've seen, or something else. And they discovered that the lower bound in this case is 1 over k squared, faster than 1 over k. And then it was an interesting problem to find an algorithm that achieved that lower bound, because classical gradient descent does not. It's slower than that lower bound. And lo and behold, this beautiful result due to Nesterov, building on previous work on momentum methods and heavy ball methods, he discovered a two-step algorithm, or two-piece algorithm. There's now an augmented variable y, and y looks like it's doing gradient descent in the x variables, and then the x is a convex combination of the last two y's. So many people have stared at this and tried to get their own intuitions for it and think about it. Now, if you see Nesterov talk, he sort of says something about modeling the surface. There are many intuitions. It has kind of a momentum or heavy ball flavor. But I'd say to this day, there's still some mysteries about this thing. And we're going to try to be digging into that mystery a bit. So the algorithm, whether it's mysterious or not to you, Does the achieve the optimal rate of 1 over k squared? That proof is not trivial. Nesterov developed a whole estimate sequence technique to prove things like that. So it's a beautiful piece of work. I often ask the audiences how many people know about this, kind of when I talk in math and computer science departments around the world. And out of 100 people, it's often like 2 or 3. And that's shocking to me. This is one of the biggest developments in the last 40 years in applied mathematics. Everybody knows what the fast Fourier transform is, and no one knows about this. And that is strange to me. All right, so since that time, which is about 40 years ago, people took that spirit and brought it into lots of other problems, mirror descent, cubic regularized Newton, and so on and so forth. And the idea of acceleration carried over. It wasn't quite clear what the technique was, or was there a general methodology being here, but kind of the spirit and some of the kind of the algebraic tricks that were carried over to other methods. These are all some of the classic gradient-based methods. There are descent methods, are relatively understood. And you can accelerate all of them. So there was this, many people contributed to this. There are many practical procedures that have resulted for this. There's many beautiful theoretical results. These are typically not descent methods. They will go down and they will come back up. They will oscillate, which is not too surprising. If you're trying to get downhill as fast as you can, you might take the curves a little bit fast, and somehow that's kind of necessarily leads to oscillation. But understanding why you should oscillate and how much you should oscillate is still mysterious in general. So there are lots of people been working on this. In fact, here's some of the recent papers on attempts to explain Nesterov acceleration in some sense. So many of these are quite beautiful. I highly recommend reading them. I really like the Chebyshev polynomial work, Moritz Hart. I like geometric shrinking and so on and so forth. But these are only typically limited for either strongly convex functions or first order methods or Euclidean spaces. And I think it's still true that there's kind of not a full understanding of what the phenomenon is. So we're going to propose, and maybe insight into it. I will hesitate to say a full understanding, but some insight into it. And the secret is going to be to go into continuous time. In continuous time, this phenomenon is much easier to understand. That makes a lot of sense, because in discrete time, you're hopping around, and there's not quite a notion of accelerate. It's not so clear what that would mean. And in fact, rates, are just as a little more mysterious. Whereas in continuous time, it's quite clear. You just have a clock, like Einstein, and you just change the clock. So when I have a continuous path, it's quite clear to think about it. And in fact, to understand acceleration, in some sense, it's easy in continuous time. And the whole problem is going to be to get back to discrete time. And when and how can you do that? And sometimes you can't. And try to develop a theory of discretization appropriate for a certain class of variational problems. And if that's familiar to you as a physicist, it should be, because that's an area going back to Hamilton, Jacobi, and Poincaré and so on. How do you discretize certain classes of physics-based differential equations? And we'll be getting there by the end of this section. Okay, so gradient flow. So widely studied in mathematics. It's a differential equation that says take the gradient and go down the negative of the gradient in continuous time. So it's a differential equation. You don't have a step size here to worry about, all right? And you can analyze the rate of this thing. Mirror descent is the discretization of natural gradient flow. All right, so there was this very nice paper in 2014 that influenced us a bit, or quite a bit, which took Nesterov acceleration and took the step size to 0 and asked what differential equation results. And they found that differential equation results. So it's second order, it's non-homogeneous, there's this funny 3 sitting there, and it has the gradient. Okay, so that's pretty interesting, and then they were able to study this and use Bessel functions to get some kind of approximate solutions, and you can see the oscillations arising from the Bessel functions, and so some insight was gathered by this. But there remains a mystery, sort of why that differential equation. And is there a more general methodology behind delivering differential equations like that? And so in some sense, what's not happened yet in this work and previous work is to think about, is there an optimal way to optimize? Right? That really is kind of the question. So these oracle bounds, due to Nemirovsky and Yudin and others, suggest that there's an optimal way to optimize. There's a lower bound. All right? And so, but it's not a productive methodology. It's an existence statement about worst case functions. Is there an optimal way to optimize? Well, to answer that question, you have to have an optimization principle that delivers an optimal way to optimize. So if this is a way to optimize in continuous time, what delivers that differential equation? And is there a principle for getting that mechanism underlyingly? All right, so if that sounds like physics language, It really should be, I think. So we're going to talk about a variational approach to delivering that differential equation, but not only that differential equation, but a whole slew of others. And ideally, get all the kind of accelerated methods out of a underlying variational principle. Okay, so here's the variational principle that we're going to propose. I'm just going to write it up on this slide. It's a Lagrangian. I'll argue why it's a Lagrangian here in a minute. But it's a functional in continuous time of position, velocity, and time, t, so non-homogeneous. The core parts of this are, first of all, the Bregman divergence sits right there. So hopefully all of you know what the Bregman divergence is. It's a way of measuring distance between x and y in some space, perhaps Euclidean, by looking at the discrepancy between a linear approximation to an auxiliary function h at x and at y. Okay, so it's that vertical bar measures the distance in the horizontal direction between x and y. If we pick h to be quadratic, this is just another way of writing Euclidean distance, but h can be logarithmic and have there's other convex functions can be used for h. All right, so that sits in an interesting place in this functional we're going to be optimizing. It's in the place of a kinetic energy. And it is a Bregman divergence between x, where you are now, and x plus a little time scaling. The alphas are not very important here, but it's a time scaling of x plus something times x dot. So it has a little feeling of look ahead. You're sort of saying, under the geometry given by h, how much cost am I going to pay energetically by perturbing a little bit in that direction of x dot? All right, so that sits there. The next important part of it is the potential energy. Again, scaled by a certain time function, but you have to have the function f in that you're going downhill on. All right, so it sits right there. So alpha, gamma, and beta are the degrees of freedom here. They are arbitrary smooth functions. There's going to be a relation between them. There's actually only one degree of freedom for getting the fast rates. Now, in the Euclidean setting, as I mentioned, h is the quadratic function. And if you plug that in, that Bregman divergence just reduces to 1/2 x dot squared. So it really is a kinetic energy. And so this looks like kinetic minus potential. So that's why we're going to call it a Lagrangian, but it's a Bregman Lagrangian in general. So here's the relationships that you need between the alphas, betas, and gammas to what we call ideal scaling to ensure that you actually achieve these fast rates. So I don't want to spend too much time on this, but let's just assume that for now that only one of the 8 alpha, betas, and gammas need to be specified by the user in setting up this Lagrangian. Okay, so now what do you do with Lagrangians? Well, you do what Lagrange did, which is that you use calculus of variations to deliver a differential equation. All right, so just to remind you, here's our Bregman Lagrangian at the top of the slide. You simply put that inside of an integral and you minimize over paths. That's the calculus of variations. And there's a sufficient condition called the Euler-Lagrange equation, which finds a stationary point of that functional. Okay, so there is the Euler-Lagrange equation. It's some partial derivatives on L and a total time derivative. So it delivers a differential equation. It's not a PD, it's a differential equation. And it's easy to do. So you can just take that object up there L at the top and take some partial derivatives and take some time derivatives, and out pops that differential equation. So let's call that our master differential equation. It's coming out of that Bregman Lagrangian. And I claim this captures a wide span of Nesterov accelerated methods. So it is second order, it's non-homogeneous with some time derivatives of alpha there, and it has some geometry here, and you have the potential, the gradient of the potential. Okay, so have we understood anything yet? So far, we've sort of gotten ourselves a differential equation. Is there something more to be understood from the Lagrangian perspective? All right, so first of all, you'd like to ask about the rate of convergence of these differential equations. All right, so in optimization theory, you do that by writing down some difference equations and using your Lipschitz constant and so on and so forth. Here you use Lyapunov theory, the very natural way to do it. So can you find a Lyapunov function for that class of differential equations? All right, and the answer is you can. I'm going to show it on the next slide. And then therefore, can you get a rate? And so we're going to get a rate with a one-line proof for the entire class of accelerated methods of continuous time. And that's already some evidence that we're on the right track here. So here is the result, that the rate goes as e to the minus beta t. Beta is one of those degrees of freedom. So we can pick the beta to have the rate we want it to. And then that'll give us a differential equation that has the beta built into it. And the proof is extremely simple. You write down that Lyapunov function right there, that epsilon e of t. You take its first time derivative and you insist that that be less than or equal to 0. And to achieve that, a necessary and sufficient condition is that you have that rate at the top there. All right, so that's already some interest. So that Lyapunov function, in some sense, as with most Lyapunov functions, could be viewed as coming out of the air. It just happens to work. But we also were able to find a systematic methodology for deriving the Lyapunov function from the Bregman Lagrangian. Okay, so that's interesting. Now, that rate seems way too ambitious. It's exponential. We don't expect to get exponential rates out of optimization procedures. We expect things like 1 over t squared, so on and so forth. Now, this is e to the something. All right, so something must be breaking somehow, been going from continuous time to discrete time if we put in an arbitrary beta. And so where is it breaking mathematically? All right, so let's first of all try to figure out where it would work. So if I don't be so ambitious and I put beta t to be logarithm of t, or logarithm of t to the, p logarithm of t, then I'll get rates like 1 over t squared and all, and we hope that we can achieve those rates back in discrete time. So let's not be ambitious and let's do that. So let's set beta equal to p log t, plus a constant, and that's going to also set alpha and gamma accordingly. And what do we get out when we make that maybe less ambitious assertion? Well, first of all, we get out a 1 over t to the p convergence rate. So gradient descent is 1 over t, Nesterov acceleration is 1 over t squared. Here we're hoping we might be able to get 1 over t for arbitrary p. Okay, let's see if we can do that, but we hope we can. And here's the differential equation. The master equation turns into that. All right, so already started to look a little bit simpler. And we sort of suspect that we're on the right route because if we put p equal to 2, we get 1 over t squared, and we get that 3 over t from the Su, Boyd, and Candice paper. All right? And if we use Euclidean geometry, we get exactly, in fact, their differential equation down here. So that just reduces to that when we make Euclidean geometry assumptions and we set p equals to 2. We also get a corresponding result for mirror descent. Okay, so this thing is recovering some of these natural or these known accelerated methods, but this thing, in fact, goes further. So let's write down p equals 2 and p equals 3 just to see what the differential equation looks like in those two cases. So there's p equals 2 and there's p equals 3. And you don't have to know much about differential equations to sort of see there's a lot of similarity between those two equations. And sort of all that's kind of changed is the 3s have gone to 4s or 2s have gone to 3s and there's a 9 instead of a 4. But it really has exactly the same form. Okay? And so what's happening here is that this Euler-Lagrangian is covariant. So this this Bregman Lagrangian is covariant. So this thing is delivering for arbitrary p exactly the same path in space-time. All right, so that's already a discovery now. Okay, so there is an optimal way to optimize, and it's exactly the same path. If you want to accelerate around that path, you just change your clock. So if Barrett's going at a certain speed according to his clock, I just use a different clock, and I go along the same path, and I'm doing the optimal thing at my rate. Okay, so in continuous time, acceleration actually is no longer a mystery. If you pick the right path, then you just accelerate by changing the clock. All right, no mystery at all. It's really, no big deal. All right, and now that goes through for a whole wide range of other problems. Some of the ones I listed, mirror descent, cubic regularized Newton, and so on. All of them have a path given by this Bregman Lagrangian, and acceleration is just changing the clock speed. All right. The proof of that is just really, really simple. I won't get into it, but it's just a time dilation story. You can just redefine the parameters, and you get this covariance property. Okay, so the whole mystery of acceleration in some sense can be viewed as reducing to the problem of how do I discretize a certain class of differential equations. If I discretize in the wrong way, perhaps I don't get out accelerated discrete time methods, and maybe there's some continuous time methods I can't discretize. Because in continuous time, I can get exponential rates. I can make the clock as fast as I want. Somehow, when I do that, I must not be able to go back in a discrete time. All right, so that's where the whole mystery comes down to. And here, we're still working on this, but there's been already some discovery. So first of all, if you try to discretize the dynamics of these Euler-Lagrange equations naively, just by using an Euler method or a explicit Runge-Kutta or something, here's an example. So I don't want to, at this point, let's suppress the mathematical details. Just, follow along at a higher level. That's a discretization of these equations. Sorry, that's the first order version of the second order equations, and here's the discretization at the bottom. If you implement that, it's not stable. It goes in and then shoots off to infinity. Okay, so here it is in one dimension, as you can see. So that's not good. You would never want to put that on the computer. Moreover, you lose the fast rate. So is there a way to discretize that is stable, provably, and still maintains the fast rate? So there is, and again, I want to gloss over details here. And there is, and the way it comes about is a way to do it, this is not the way to do it, is to sort of imitate what Nesterov was doing. Nesterov kind of took a couple of equations which involved a convex combination, a gradient, and a mirror descent step. And people have noted that kind of syntactically that's what's going on there. If you now think of that procedure, that three-step algorithm, a three-piece algorithm, as a discretization method for differential equations, people haven't thought about that, but you can think about it that way, all right, then you can write down a discretization that in fact provably converges at the fast rate, 1 over k to the p, so you're at 1 over t to the p. In discrete time, you're now 1 over k to the p. And here is the discretization. Again, I don't want to get into details, but it has kind of a Nesterov-style flavor. For the general case, it involves 3 sequences: an x, which is a convex combination, a mirror descent step, and a proximal step. There is a proof of convergence of this. Turns out the proof of convergence is itself a Lyapunov proof, and in a follow-up paper here, Aisha Wilson has written a very beautiful paper showing how you can derive the discrete time Lyapunov function from the underlying continuous time Lyapunov function. And that so allows her to dispense with estimate sequences altogether. So it's now just a pure Lyapunov theory, can do the whole story if you don't like estimate sequences. Okay, so there it is. So to summarize what's happened so far, this is kind of the landscape of the literature. People have worked on gradient methods for a long, long time, and we're talking now about higher order gradient methods. And you can do them in continuous time. So that's been known, for a long time. And if p is bigger than 1 or 2, you get these higher order gradient flows. All right, and so they are a particular scaled version of the gradient with a scaling that involves a dual norm. All right, and so here's what Nesterov did and others, is to take the discrete time version of that into accelerated methods. And you can now do that for bigger values of p than was considered. Nesterov did p equals 2 and p equals 3, but you can do this for arbitrary p. And then moreover, you can go into continuous time with acceleration. And the right way to think about that is that you have an underlying variational principle. A particular Lagrangian delivers a differential equation that can be studied as a mathematical object. That object, in fact, has other properties involving various invariances that are familiar to if you're a physicist. Okay, so the last slide here, I'm going to get down to the very bottom here quickly. So you can now ask, is there a more general theory of discretization here, lying here? So this paper, which we published last summer, was just sort of cooking up a discretization method based on looking at Nesterov. But is there a more general theory? So if you now go and learn about the area of geometric discretization or geometric based differential equation discretization, that exists for like 100 years. And it usually starts from a Hamiltonian formulation, not a Lagrangian. So in the Hamiltonian formulation, in some phase space, you're conserving various things as you move along these differential equations. Energy, momentum, various exterior forms. And if you want to discretize in a smart way, according to a physicist, you want to discretize in a way that still conserves those same entities exactly. Even though the path is now approximate, certain quantities like momentum and energy and so on are being conserved exactly. Because if you're going to run something like a simulation of the cosmos for a long time, you might start to lose the path a bit, but you don't want to start blowing away energy and momentum. You're just doing the wrong physics. So Hamilton, Jacobi, and Poincaré and others worked on that, and they sort of solved it. So the whole area of symplectic integration emerged. There are beautiful books on this that figures out how to integrate certain differential equations, not by simply just taking a local hop, but by looking at kind of a volume element around a path and preserving that volume element as it flows around. Okay? From that emerged the whole field of symplectic geometry, and to this day, very active area in various branches of mathematics. So why am I bringing this up here? Well, because Nesterov acceleration looks suspiciously like symplectic integration. All right? So for a while, I thought that it was exactly symplectic integration of this Bregman Lagrangian. That's not exactly true. So you can do a symplectic integrator instead of Nesterov, right? When you do that, it does achieve the same rate as Nesterov, but the beginning Nesterov is a little bit faster, interestingly. So we looked into that, and so Nesterov is kind of strange in a way. It has a dynamical flavor to it, momentum, but it also has that convex combination, which can be viewed as just a rotation of the coordinate system. You know, dynamics flows and oscillates. Dynamics doesn't rotate coordinate systems. So in that sense, that part of Nesterov is not just pure dynamics. It's not just a momentum method. All right. So if you think about how to try to put that sort of aspect of Nesterov in back to the symplectic integration framework, there's a way to do that. All right, so in the paper we're just working on right this moment, we figured out how to do that. And so we now have a new method which is basically symplectic integration with an extra ingredient that does achieve the same rate as Nesterov and actually beats Nesterov early on. It's much faster than Nesterov, and then they achieve the same rate. All right, so at this point I think that Nesterov is really a discretization method for differential equations. And it's not the only one, and it's not even the best one. All right, so I'm going to stop there on that topic. I could go on, but there was a couple of other things I wanted to talk about. Let me just see, though, if there are quick questions about that before I move on. That's the bulk, that's the biggest part of the talk, but I have some other things to talk about as well. All right, if not, store up your questions. Yeah.
What are the conserved quantities here?
The conserved quantities are abstract. They're just basically differential forms in a certain differential geometry sense. They're worthy of study. In fact, there's a lot still to do here, which is more about, okay, you've recast the mystery up in kind of a cloud of new formalism involving Hamiltonians. By the way, how do you get the Hamiltonian? You take the Lagrangian and you do a Legendre transform. So just traditional, nothing mysterious there. But you know, where is that Lagrangian coming from? Where is that Hamiltonian coming from? Why? It does conserve certain invariant, you know, certain exterior forms. Why are those important for optimization? So one would like now to tie that sort of story back. We now have more of a constructive mathematical view of optimal optimization, you know, sort of back to the oracle theory or something about, is it motivated directly from that? So there's still quite a bit of mysteries here. And in fact, this whole part of the talk, this is brand new work. There's just tons of new mysteries. So if you like differential equations and optimization, you know, there's tons of things. In particular, the stochastic case, you want to think about diffusion versions of this. That's all, everything so far has been deterministic. You know, stochastic symplectic geometry, you know, very interesting things could be looked at as well. So we're doing that, and I just welcome anybody joining in. This is a brand new little area, I think. All right, let me move on. You can store up other questions, and we'll see where we get to. Okay, so let's now indeed bring in some stochastics. So this is work with Li Wah-Lei at Berkeley, very recent work. So one of my favorite topics in the last few years has been this notion of variance-controlled stochastic gradient methods. So I think you all know how important stochastic gradient has been. It allows you to go much, much faster in each step of an algorithm instead of waiting to get a whole gradient. That's great, so you make progress much, much quicker. The rates, on the other hand, go down in terms of the approach to the optimum, not on wall clock time, but on step time. And moreover, the stochasticity starts to hurt you as you get close to the optimum. You've got to somehow turn it off. All right, so an elegant way to do that has been discovered by many people. Francis Bach and his group, I think, were one of the people that started this. Tong Zhang and many others have contributed to this. So again, kind of a standard setting here. This one is going to be, in particular, a sum. The functions are going to be composite. They're going to be sums of finite sums. And we're going to make kind of the usual assumptions of smoothness and Lipschitz. So we'll look at both the strongly convex case and the non-strongly convex case. And now let's talk a little bit about computation complexity. Let's assume that getting the function value and the gradient is one unit of cost in our model. And the t epsilon is going to be the minimum cost to achieve a certain value of epsilon. All right, worst case analysis has been done for many of these algorithms. In particular, one we'll focus on is SVRG, stochastic variance. What is it? SVRG. Blah, blah, blah. What's the R stand for? Reduction? Yes, variance reduction gradient. Thank you. Tong Zhang and colleagues have worked on this. All right, so it's for the strongly convex case, it's fast. It's got a log of 1 over epsilon there. That's very good. But it has an n there. That's not good. So, you know, if the finite sum is growing, it takes you more time, and that's not favorable. You don't want that. That shouldn't necessarily be the case. Okay, here is SVRG if you haven't seen it before. What it does is basically, it's gradient descent, but it does variance reduction by it's stochastic gradient descent, occasionally computing a full gradient, kind of resetting, and then using deviations off the full gradient as your stochastic gradients. All right, so just in the notation here, it takes a g as a full gradient over the entire data set, computed from time to time. This is one epoch, so it does it per epoch. All right, then it's going to do a little batch of operations. That is, the size of the batch is chosen uniformly from 1 to m, where m is set to n in the beginning. Then you randomly, stochastic gradient, you randomly pick an index, you compute a stochastic gradient, and you subtract off the discrepancy between that and g, where it is evaluated at the initial point when you started the epoch. Okay, and then you just do a gradient step. So that is SVRG. So here's some theory on this. So if you take Nesterov's AGD, if you take stochastic gradient SVRG, and then a recent version of that known as Katyusha, Alan Shu's work, here are some of the results for general convex and strongly convex. So in the strongly convex case, you can start to get the fast factors of log of 1 over epsilon. SGD puts, unfortunately, a 1 over epsilon in front of that. Kappa is the condition number for these things. SGD is the only one that doesn't have an n in it. And that is one of the reasons everyone likes SGD. It's not a function of n. All right. Katyusha has an n there. That looks unfavorable. I must say, though, that in practice, that algorithm is quite fast. It's faster than these bounds would suggest. These are worst case bounds, and Katyusha does seem quite promising. Okay, the acceleration is coming out of this part of the talk as going from epsilon squared. That's time. That's unfavorable. That's big time. Epsilon's a small number. Going up to square root of epsilon, more favorable for the accelerated version. SVRG applies to strongly convex, and it doesn't. There's no theoretical result for general convex. You can apply it, but no guarantees. Okay, so that's kind of the existing literature. All right, so first thing we've done is to move away from worst case bounds. We're going to talk about randomized algorithms, and the randomization is going to actually get us gains in computational complexity. And we're going to put in a geometric distribution at a particular place. That choice turns out to be actually critical to get computational complexity result. So we're going to be able to get algorithms ideally, which are going to be independent of n. That's going to be too hard to achieve, but something where n doesn't hurt you is what we can achieve. And we want to beat worst case bounds. Okay, so here are the theoretical results. I'll show you the algorithm in a minute. But SGD, just for reference, is sitting up there for general convex and strongly convex. I don't want to spend too much time on this, but this is important in practice. Tuning friendly for us means that the step size is determined only by L and mu, which are things you might be able to get your hands on in practice. If step size is something depending on how far you are away from the initial optimum, for example, that's true of some algorithms, or other things you can't know in practice, we call that not tuning friendly. So SGD is not tuning friendly. The step size is you have to know how far you are from the optimum. Anyway, 1 over epsilon squared to 1 over epsilon. This new algorithm, stochastically controlled stochastic gradient, is written right there. So again, we sort of look very much like SGD. In fact, basically kind of the same. But the computational complexities will be much reduced, as you'll see in a minute. But then we've gone on very recently to a new algorithm we're currently calling SG+. There are 2 versions of this involving different ways of choosing the tuning parameter. Let me not spend too much time on that. But now notice that instead of the n dependence, it's gone to log n over n. All right, so there you go. That's favorable now, because that's going to go away as n gets large. It's not going to hurt you. It's not growing in n. It's actually decreasing in n. So we get 1 over epsilon log 1 over epsilon here. You can actually put a square root around that in this case of a different procedure that has a less realistic tuning parameter setting. So these results are in fact beating the oracle bound, and the reason they're beating the oracle bound is because these are expected values over the randomness in the algorithm and not worst case values. Here is the algorithm, just comparing to SVRG. It's somewhat similar. It's going to, first of all, pick a random set of size b, where b, so a huge data set I, b is going to be a random subset. So we're going to compute our full gradient, not on the full data set. That's too costly. We're going to compute it on a stochastically chosen subset, which you can do much cheaper. So that's going to, in some sense, hurt you in terms of variance reduction, but it's going to help you with respect to computational complexity, and the randomness actually is going to further help you in terms of convergence rate. All right, we're going to then set up a parameter gamma, which is going to be decreasing in a particular way, and then we're going to draw in from a geometric distribution depending on gamma, and that choice is very important. The analysis depends heavily on that. Now you go in little mini batches of size n, which are these geometric sizes, and then you do stochastic gradient just as before. Everything's the same, except your gradient is now based on the smaller subset, the little mini batch, if you will, for the full gradient instead of the full gradient. Okay, so there it is. It's really patterned off of SVRG, but is a computationally much more efficient because you're using the set B rather than I. Okay, so just a little bit more details on the particular ways that this thing has been set up. Okay, so there's the algorithm and there is the analysis. These are really favorable analytic results. We are kind of now spending more time on actual empirical work, but the theory is strikingly solid. So just to summarize there, instead of calculating a full gradient from time to time, which is what that literature has been doing, both SAG and SVRG type things, we're not doing that. A really big data sets, you don't want to do that. So you take a subset to compute your reference gradient, and then use that in the context of a stochastic gradient thing, and it's possible to do get tight theory on this. Okay, that was part 2. Let me move on to part 3 and check my time here. Okay, so gradient stuff, stochastic. Now let's talk about asynchrony, which is kind of, you really have to be brave to do this. And Horia Mania, the first author here, is brilliant young researcher from Romania who really loves getting into details. And so when you talk about asynchrony, you have to really worry about what part of the machine knows what answer when, and you don't ever have a consistent notion of state anywhere, and you have to worry about all that. So this kind of harks back to the 1980s. People like Tsetsiklis and Bert Sikas at MIT did a lot of work on this, and that whole community spent a lot of time. There's a book on it, and it still remains to this day an active area, but just not as active as it probably should be. So let's talk about the whys and wherefores of asynchrony, and then get into some analysis of this. So there's a whole bunch of other colleagues here, all at Berkeley, although some of them are moving away. Dimitris is now up at Wisconsin, and so on. All right, so these are Horia's slides, so the format's going to look a little different. He likes black backgrounds for some reason. All right, so let's now be a little bit more engineering oriented. The talk, in fact, is going from more towards the engineering side. In reality, if you run SGD, even though it's got favorable properties, although it can be beaten, it could be hundreds of hours on the sort of the modern, large-scale deep learning kind of problems. So how do you get around that? Well, you parallelize. Okay, so people have tried the GPU parallelization and then as well done kind of real full distributed parallelization. But as a theoretician, that opens up all kinds of now extremely interesting challenges and opportunities for theory to be done, because if you just naively do this, which is what many, many people do, all the guarantees that you had from the not parallelized algorithm are gone, and you can hope that it works, but it may or may not work. All right, so this is really, I think, critical for theoreticians to be involved in this whole issue of how do you parallelize. Again, in computer science, there's not a general theory of parallelization, so in some sense we have to develop our own for our purposes. All right, so just Horia has done some nice little slides here, just sort of suggesting that I have data points on the left there. Every data point, this is maybe a sparse setting, is when I do the gradient, going to adjust some part of the model. The model is just a list of parameters. So if you think of the gradient adjusting, many of the gradient parts will be 0, and some of them will be non-zero, and there's going to be some conflicts. All right, so this perspective is not all that new, but it's not that common, which is that when you take an algorithm and you run it on some input, and then you put it into a machine that's asynchronous, has multiple processors all hitting the memory at different times, and no control over that. All right. That's all in some sense deterministic, but we're ignorant about how the machine is really working. So we're going to model this using noise. Now you could just take asynchronous algorithm plus noise. That wouldn't lead to any help in the analysis. All right. But the way that you can analyze this is get rid of the asynchrony by imagining noise is being added to the output of the algorithm, and then you put the result into a serial algorithm that you can analyze. And if you choose that noise correctly, you can actually have equality here. You can get the exact same results that you get under the asynchronous algorithm in this analysis. And moreover, this is going to turn out to simplify many of the analyses that have been done very, very painstakingly with specific versions of asynchrony. Okay, so here is that kind of conflict I alluded to earlier. What if 2 data points in parallel on 2 different processes are trying to write to the memory, and they're adjusting the same component of the parameter vector? Well, what do you do at that point? So either you coordinate and you lock that site and only allow one of them to write at a time, or you don't care, you let the overwriting happen, and you hope that maybe the overall effect of that is small and can be controlled. Okay, so again, literature on this going back to the 60s through the 80s, and being renewed with all the new hardware. The hardware I have in mind here is shared memory and multiple processors. So very, very common modern architecture. In fact, in your laptop nowadays, that's what you have. You can either lock or you can not lock. All right, so there's this nice paper. I guess I say Steve here. Steve and his colleagues proposed this lock-free formalism called Hogwild back in 2011. So they just sort of said, let's not worry. Let's just try. Let's let it overwrite happening and do some analysis to show that that's not going to hurt you under certain conditions and try to understand those conditions. So you basically read shared memory, you in parallel compute a bunch of gradients, and then bang, you let them all in parallel hit the memory. And here's some of the kind of results they were able to get, speed ups, quite significant ones over competing algorithms. And that, caught a lot of people's attention, and some of the state-of-the-art large-scale projects are based on Hogwild. All right, so the first thing we've tried to do here is to reanalyze Hogwild. The analysis in that paper was quite complicated, and an approximation was made. Can we get around that? All right, so first of all, if you think about this setting, the reads and writes, in fact, Horia had this animated, and I've turned it into PDF, it's lost the animation, but the reads and writes are overlapping in complicated ways. And when a processor looks at the memory, it'll read something, then it'll take that in and do some operation, then write it back out. In the meantime, some other processors might have written in there, and so there's no actual shared state. Everybody is having a slightly different version of what the state is. So there's no concept of an iteration either. The synchrony is gone. All right, so you can think about that as that I'm at some point x naught. Ideally, I go down the gradient at that point. All right, but the processor who are taking the gradient with respect to that data point has gotten a perturbed version of x naught because of the asynchrony. And so it's sitting over in a different place in the space, computing a gradient at that point, and then writing it back. So that, in fact, x naught is still sitting in the memory. The processor's got the wrong idea of it. So that adds that displacement to x naught, and you get an answer right there. Okay, so you would have liked to have gone there, instead you've gone right there. And the whole point is then to analyze that, do the probability theory to analyze that. Okay, so again, I don't want to get into too many details here, but this perspective can be carried through for Hogwild, and the resulting analysis is really quite simple. It's actually just a page of analysis instead of the multi-page analysis, and it's exact. There's no approximation being made. And so kind of what's happening is you just kind of think through the graph of interactions here that you are, after t-process samples, you think about what's in the memory, it's gradients based on these perturbed answers. You now can ask for a particular, say, x5 minus x5 hat. That's an error, and you'd like to bound that. Well, you look at x5, which might be on CPU 2, and you look at what it did when it actually updated. It looked at gradients from these previous updates, which were done at wrong points. And it itself is doing it possibly at a wrong point. So you read something from memory at that point, and then you control this error. And you think about all the gradients that it can depend on, and you just look at kind of the overlap in one of these kind of Lamport-style diagrams. All right, and then you analyze all of these things based on whatever happened when the thing read the thing from the memory. So what a lot of these previous analyses have done is thought about what happens when you write to the memory and try to bound things there. The right way to do this is what happens when you read from the memory. That turns out the stochastics can be done exactly and simply there. So, you can get a single quantity that characterizes the amount of overlap. It has to do with the degree of what's called the conflict graph. Conflict graph is, two data points conflict if they share a parameter in common when they write. So you can draw that graph, and then you can find the degree of the average degree of that thing. That determines the probability of conflict. And if you're never doing more than that number of samples in parallel, which has to do with the number of computers you have, then the number of conflicts you have is constant in expectation. So we're then able to prove a theorem for Hogwild. It's basically the theorem you would hope that it achieves exactly the same convergence rate as serial SGD under this condition on the conflict. Okay, so that's the kind of the theoretical support for this, and some of the details on comparison to the original proof. Okay, so that framework is also generative of other new ideas, and again, I'm pulling things from a longer talk, but we've done a version of this for asynchronous coordinate descent. I think Steve is maybe talking about things like that on this conference. And there's a new algorithm called Cro-Magnon, which is of SVRG, but sparse and asynchronous. And this has been empirically quite successful. So we have a paper on this. And implemented on 16 threads led to 10,000 times speed up over serial SVRG. So really, really significant improvements. Okay, so that was part 3. And each part is supposed to get, I'm on a decreasing schedule here. This should be even shorter. How am I doing on time, though? You're going to tell me, Mike? 10 minutes. Good. That's going to be perfect. Okay, so this is yet more engineering-oriented, but still theory is guiding all of this. So now we're going to the full distributed paradigm. I don't have a shared memory anymore. Every computer has its own memory. And the asynchrony is going to be much, much higher because I'm really far apart in network space. Right? So what kind of theory and what kind of procedures can you develop here? So this is the area where you really start to have to think about more of your algorithm. What is the algorithm you're trying to do? Not just take an existing algorithm and prove some things about it. It's not going to be the case that existing algorithms will necessarily work in this situation. So again, lots of colleagues here. Ginger Smith at Berkeley has taken lead on this, and we have now a long archive paper summarizing several lines of research that came together in this thing called COCO. So the key word here is communication efficient. So if you followed linear algebra in the last decade, that's been the revolution in linear algebra, numerical linear algebra. 20 or 30 years, it seemed like it was done. They had blasts, they had the most efficient thing you could possibly do for eigenvectors and so on and so forth. And then suddenly everything is now distributed across a network and you have to avoid communication. So they rewrote the whole textbook on numerical linear algebra, doing it communication avoiding. So same issue comes up here. How do we avoid communication in our literature if we're going to actually go to full distributed paradigm? Okay, so you can look at kind of existing methods we have, parallel distributed first order, that's all great, but now we've got to make this fully distributed. And again, there's kind of a naive way to think about this is that you can either lock things or not. So you never communicate means that you let one of them do its work and then you wait, you synchronize, or you can always communicate and have a huge communication cost. So somehow you want to be in the middle, and how do you develop a formalism that allows you to be in the middle? Mini batch is kind of the idea that as people gravitated towards, and kind of in some sense what we're trying to do is find a mathematical way to think about mini batch ideas. So mini batch is just that on every one of my machines I put a I put some of the data on each one of the machines, and then I pick a relatively big but not too big subset to work on at any given time. So that I have a certain amount of everything is happening in parallel, but I don't want to get things too out of date that when I bring them back together, I'm going to have asynchrony, out of dateness issues. Okay, so long story short, the way to go to do this and move beyond SGD, which is where most literature has been, is to in fact go to Primal-Dual Framework. So this is not surprising if you know about things like ADMM, that to decouple algorithms, it's very useful to go to the dual, because in the dual, the constraints from the primal tend to get decoupled. They tend to be box kind of constraints instead of non-box constraints. So going to duality is critical for us as well. When we go to duality and then we do another upper bound on the dual problem, that's going to be the key, then it's possible to have yet more decoupling so that you can do a lot of progress in parallel without ever synchronizing. And after that happens, then you can bring things back together, and the amount of staleness can be bounded so that you can still make progress and get a theory. Here is a kind of a primal dual setting for a kind of standard machine learning problem. There's a regularization, there's a sum of loss functions. Here is the dual for that. Hopefully that's familiar. There's our conjugate dual sitting over there. That problem is now more decoupled relative to that, but still somehow not enough. And that's kind of where ADM stops, is sort of just at that. But we want to do a little bit further than that. And so without getting into too many details, here is a variational expression which is further decoupled these problems. So it's a further upper bound on the dual that is further decoupling. So I want to finish, so I'm not going to get into this technically, but just you can look at the paper. When you do this, what you're going to do is on each one of the machines, you're going to go in parallel, and you're not going to have to worry about synchronization. You're just going to do fresh updates at all times. So in parallel, we do a lot of work on our mini batch, and then we bring things back together and average. That averaging is actually not desirable. That cuts down the overall effective step size you would really like to add. If I made progress here and I made progress here, in some sense, I'd like to be able to take the sum of the two progresses. And in a follow-up work, we figured out how to do that, to add instead of average. But I'll just talk about the average. So here is the overall framework. It's a local primal dual method. What you do is you dualize, you do a further upper bound, and then on each local machine, you take any arbitrary dual method. It could be dual coordinate ascent, it could be dual gradient, dual whatever. We do that on each machine, and then the overall framework tells us when to resynchronize and bring things back together. Okay, so again, let's not get into details at this point. And here's the theorem. Which says, roughly speaking, you can look at details, but it says that the overall procedure inherits exactly the convergence rate of the local procedures. So if you proved a convergence rate for your dual method on each machine, the overall procedure will not lose that. Okay, so that's about as strong a result as you can get. So there's various constants to kind of assure that this is true, but here's our general form of our theorem. The main part I wanted to get in this, I'm about to finish, is in this part of the talk, is just to say that this really does work in practice. Here's some examples. ImageNet, we've got 32,000 data points in this particular version of it, 160,000 features, and we're doing this with 32 workers. Let me skip over that. And here are some examples of results. So, SGD, mini-batch SGD, mini-batch coordinate descent are the green and blue curves. And the new one, the cocoa, is right there. So people in industry have noticed, and this is being picked up and used quite a bit in industry. Let me skip over some of these slides so I can get to where I finish. And in fact, here's the main thing I want to point out. There is now an open source community around this, and this code is being developed not just by us, by other people. And there is the GitHub address for that. So the attempt here is to make a sort of commodity out of primal dual optimization. In some ways, ADMM did this, but ADM is much slower than this. This is completely different in terms of overall speed. And so if you're interested more on the system side of this, please contribute. There's lots to do here. Okay, so just 30-second version of this. This is work that we're about ready to publish this week. Chi-Jen Rongi, Sham Kikade, and Pranith Netrapalli, talking about avoiding saddle points quickly. So saddle points are really, really important. Many problems that we have, there's kind of a global optimum. There's a ring of saddle points. You start out here, you get close to the saddle point, you get stuck for quite a while, and then eventually you get out of the saddle point and go down. So the learning curve looks like this: come down flat for quite a while, and then you get to the answer. Neural nets seem like they have something like rings of saddle points. So you start out here, you get near a saddle point, it kind of keeps you there for a long time. You break free finally, then you hit the next ring, and you're now stuck again, and then finally get down. The learning curves go like this, they flatten out, they go like this, they flatten out, and they go down. If it's true that sort of many local optima are good in many of these systems, so for some of that systems that's provably true, for like tensor completion, phase retrieval, and maybe for neural nets it might be true. It's still, people are arguing that. Then avoiding saddle points is the whole problem. Okay, and so you'd like to get a rate for an algorithm to avoid saddle points. So it sort of charges through the saddle points. It doesn't get slowed down too much. If it gets slowed down too much, you wait for 100 hours, you're maybe still stuck near the saddle point. All right, so long story short, here's my last slide. This is just from the paper we're currently working on, is that under a certain definition of the nature of the saddle points, it is possible for just a gradient-based method, that's this work here, to have the same rate as stochastic gradient descent, 1 over epsilon squared, and pay a cost which is only polylogarithmic in the dimension. Okay, so that is by far the most favorable of all of these results here. If you go to Hessians and Hessian vector products, you could also avoid saddle points quickly. You get epsilon squares, and even if you're like really, really work hard, you can get epsilon to the 7/4, right? But you're logarithmic in dimensionality there, and you pay a big computational cost. All right, so this gradient method, I'm not going to tell you what it is other than to say it's something like this. It's stochastic gradient with an extra little boost of noise whenever the gradient gets small. And if you do that in the right way at the right time, you basically get out of the saddle point and a little bit, and then roughly speaking, the power method does the rest. It kicks you out exponentially fast, and you don't get brought back in. All right, so by a tweak on gradient descent, you can actually avoid saddle points quickly. So we're trying to work on paper there. All right, so that's the summary. This is just kind of the last sort of 10 years. One of the things I work on, I just think that bringing stochastics together with optimization is kind of one of the big problems of our time. But I think most of the hard problems are open. I really think that this is for the young people in the room. There's just fantastic challenges here if you're kind of mathematically inclined. So read all the things about deep learning and be impressed by what people there can do. That's all empirical. But really, there's a whole need for kind of fundamental concepts, lower bounds, how diffusions work, how can you go fast, how can you be asynchronous and all that. In many ways, we're just kind of stitching together things and getting little insights, but I think we're really missing some of the deeper insights that can be gotten here. So I'll close with that. Thank you.